right, so this is high performance computing is my new field, parallel computing. When I left Tel Aviv University and Muli, I thought I'll leave behind many of the things I loved, reductions, PCP, error correcting codes, expanders. As it turned out, they were quite useful in my new field. What you see on the top left is Summit supercomputer, the fastest to date, working at the rate of about 120 petaflops per second. And I'm trying to help making those computers fast and robust. So peta is 10 to the 15th, so kilo mega. All right, sorry. Exa. All right, so these are the next generations. They are being built, planned and built as we speak. The European Union has invested 1 billion euro. US, China, India, other nations are investing in those machines at the same, or making similar commitments. And the main objective, well, the original main objective was to replace nuclear testing, but we enjoy that for those machines for science, for global warming research, bioinformatics and drug design, physical simulation, engineering innovations, and many other purposes. All right, so here's one of the two main challenges of these large machines. They make errors. So your average laptop makes an error, either a soft error, 1 + 1 equals, well, not 2, or hard error, that's the blue screen of death, about once a month. That's usually okay, but scale it up to an exascale machine, you get an error every second. So this is not something you can keep ignoring or living with. If you want to utilize your machine as one big machine, rather than use small chunks of it, then you have to find ways to make computation trustworthy. So this is one big challenge in supercomputing. And the other challenge is how to actually utilize those machines and make them perform well. There are two kinds of cost. One is the arithmetic cost, which we are more used to in the theory community. The other is the communication cost, or what we call here the I/O complexity. We can think of two models. One is the sequential model, where we have small, fast memory and infinite memory, and the communication is moving data between those two layers. All computations are performed on the fast, small memory. And we can think of a parallel or distributed machine where we have p-identical processors, each with local memory of fixed size m. And this is all the memory you have, and you need to move data around in order to perform communication. And the running time depends on the number of flops here, number of flops times some parameter which is machine dependent, and the number of words or bits you communicate times some machine parameters. And let me ignore the message issue. Well, CPU advances at a rate of about 60% a year. Communication advances at much slower exponential rate. That means that even applications and algorithms that are not communication bound today may become so shortly. So the objectives here are twofold. One is to come up with lower bounds on the I/O complexity, on the communication cost, and the other is to find algorithms that attain those lower bounds. If you do that and then you implement them, you are more likely to find faster algorithms. And one of the core questions is there a single parameter that determines this I/O complexity? First paper we tried to publish on my new field got this review. The lower bound proof is easy once someone shows you how to do it. I'm still not sure if it's an insult or a compliment. In a way, it's a bit like the definition of NP. All right, so here's the proof. This is something we are not used to here so much. So this is a strong scaling plot. X-axis is the number of processors. Y-axis is the performance. So up is good. And what you see here is a problem of a fixed size matrix multiplication of matrices of dimension about 100,000 by 100,000. And the green line corresponds to ScalaPack. That's a standard library for multiplying matrices on supercomputers in parallel. And this is a newer algorithm that takes into account communication cost, I/O complexity in a better way, minimizes communication, and so performs better. What you see, the dotted line here, this is the machine. The dotted line here, this is machine peak. So this is just the power you have on your machine. And then the blue lines are algorithms that use Strassen's algorithm. Since the y-axis is normalized by n cubed, they can go higher than the machine peak. And the red line is our algorithm, which up till recently was the fastest matrix multiplication. I'll explain how we got to that algorithm, and it's not by being very good programmers. I'm not. All right, so this is classical matrix multiplication, 3 nested loops. If this is what you implement on 2-level machines, the number of flops is, of course, theta of n cubed. The number of data items that are being moved, the bandwidth cost, is theta of n cubed as well. You can easily improve that by using 6 nested loops. So working block-wise, where the size of a block fits the memory. So if 3 blocks exactly fits your fast memory, then you have 3 nested loops of a block algorithm. And then once you have 2 input blocks inside your memory, you don't perform any more communication. So the total communication cost is n over square root of m. That's the new dimension. Cube times reading and writing a block. Can we improve that? All right, that's the parallel. Let me ignore that. Can we improve that? So the answer is no, and there's a lower bound by Hong and Kang from 81 that says that up to a hidden constant, this is as good as it gets. And the same goes with parallel algorithms, where P here stands for the number of processors in on your machine. And this extends to many other algorithms in linear algebra and graph algorithms, practically everything that smells like 3 nested loops. All right, how about a bit more complex algorithm? Let's consider Strassen's fast matrix multiplication algorithm. Let me just quickly remind you, Strassen showed how to take 7 linear combinations of the 2 inputs, multiply them pairwise, and then with few more linear operations, extract the matrix. So this is for a 2-by-2 matrix. You can apply that as a scheme for n by n matrix by splitting the matrices into n over 2 by n over 2 blocks, and interpreting additions as additions of blocks, so element-wise additions, and scalar multiplication you interpret as recursive calls. And this gives you that recursive relation, which solves to n to the log base 2 of 7. So the exponent is a little smaller than 3. That's good.
Upper matrix multiplications were implemented?
Sorry?
Do you know if Like a sequence of matrix multiplication.
Yes. So there's a sequence of matrix multiplication algorithms. Thank you. And the idea is the same. You need to have a base case of certain size, and if you know if you can solve the base case size with fewer than cubic multiplications, the additions don't count, then you're good to go. So this is an algorithm, this is an algorithm too, and this is an algorithm too. But from here on, at least from my new perspective as a parallel computing person, these are not algorithms from here on. And the reason is that the base case size here on is larger than the number of particles in the universe. And even in those it's pretty large. So in parallel to this competition of making the exponent as small as possible, there's another competition where people try to make the exponent as small as possible, retaining the base case size reasonable. OK. So here are some I/O complexity lower bounds for these kinds of algorithms. So this is the classic case, the classic matrix multiplication case, which we already saw. This is for, the case of Strassen. So it has the same form, but with log base 2 of 7 in the exponent instead of 3.
So just intuitively,
yeah.
Why? I mean, a priori you would think that for communication, addition is not cheaper than multiplication. Why is it like the case that Strassen helps you also save in communication and not just computation?
I'll give two answers to these questions in the next few slides. All right, and in the general case, if we have some exponent of the algorithm, the fast matrix multiplication algorithm, then it plugs into the equation. How do you do that? You take the computation graph of your algorithm, and you try to study the expansion properties of this graph. So take some subset of the vertices and OK, the computation graph, let me just remind that's the circuit of the graph. So you have a vertex for every input and output argument, and a vertex for every intermediate value, and direct edges according to direct dependency. Take a subset of the vertices that correspond to a time window or to the computation performed by a single processor in your parallel machine, and then look on these two sets, RS and WS. RS corresponds to all vertices that are outside of S but have ingoing edge into the set S. WS is the set of vertices inside S that have edges going outside of S. These correspond to elements that are either needed to be read by S or written by S. And therefore, they correspond to communication. So if we know how to perform edge expansion analysis for this graph, or rather small set edge expansion analysis for this graph, then we can have a lower bound on the communication cost, on the I/O complexity of the algorithm. What is the graph? So for the base case, it looks this way. So we have, these are the inputs, the two by two matrices, the linear combinations, 7 linear combinations, pairwise multiplications, and then outputs. And you take one recursive step that's like multiplying the graph, duplicating the graph 4 times. And then rather than having multiplications here, that's like plugging in the graph of the previous recursive step. And this goes on. And the graph has nice recursive structure, and you can analyze it in a zigzag-like way. And all right, so this is what you get. And yep.
Are these lower bounds tight?
That's the next question.
Are there algorithms that train these bounds?
All right. So for the sequential case, they are, and the algorithm that attains those lower bounds is just the recursive algorithm, the simple recursive algorithm. For the parallel case, parallel machine, we already had an algorithm that had that exact bound, and the question is, how do you attain the bound for the fast matrix multiplication algorithms? And this is the answer. So what you do at each step, you either take a BFS or a DFS step. So what does it mean? You have 7 sub-problems for multiplying A times B. That splits into 7 sub-problems. You can do one of two things. Either take your processors and split them into 7 equal size sets, so 7 sets of size P over 7, and work in parallel, or take all your resources and work one problem at a time. These are the two options. One uses more memory than the other. You need to decide which one. You are always better taking the BFS step if you can, if you have enough memory, if you did not exhaust the local memories of your machine. So this is the algorithm. If you have enough memory and more than 7 processors, or at least 7 processors, then you take a BFS step. Otherwise, you take a DFS step, and this algorithm attains the lower bounds. And this is how we got that red line up there. All right, questions? All right. Can we do better? So this is like asking, are you into constants? Because we know we are optimal. All right, let's recall Strassen's algorithm is order of n to the log base 2 of 7, and the leading coefficient is 7. 2 years later, Vinograd obtained a leading coefficient of 6, so reduced the leading coefficient. And he did that by using less linear operations. So that's the first answer to your question. And can we improve on that? So the answer is no. We have a lower bound by Probert that says that every fast matrix multiplication with a base case of size 2 by 2 requires at least 15 linear operations. Then last year, with my PhD student Eli Karstad, we showed that we can. So we reduced the number of linear operations from 15 to 12. Right. So if this seems confusing, it's just because it is confusing. There seems to be a contradiction here. There's a lower bound, and there's an algorithm contradicting the lower bound, and the lower bound is correct. All right, so what do we do? All right. The thing is, there was a hidden assumption in Probert's lower bound, which was fine with all previous fast matrix. Sorry? 12, exactly. Sorry. OK, this was the question. Sorry. All right. All right. So here's the idea of the algorithm. I'll say it right now. So the hidden assumption is that you don't change basis. And the idea of the algorithm is to change. So the low bound assumes that the matrices are in the standard basis. What you can do is you can take your input matrices A and B, transform them into a new basis, then apply some bilinear algorithm, which is not matrix multiplication. It's some other bilinear algorithm, which requires fewer linear operations, and then perform another linear operation, and miraculously together, you merge together, you obtain fast matrix multiplication.
But
Do you count the linear operations for transformation of bases?
You do. So that seems like a problem because changing bases is matrix multiplication. So sounds like we just pulled the rug. Or the thing is that with some bases, you can do better than n cube. You have FFT, Hadamard. You have several bases. And luckily, this is the case here. So you can do these basis transformation in a quick way, rather than in n cube time in order of n square log n, where the leading coefficient is 1. And these are the matrices. So these are the 3 matrices corresponding to the bilinear algorithm, and these are the basis transformation for the base case. And the recursive combination of them is in what you would guess.
So can you explain why it's easier to do the multiplication in the new bases?
Say again?
Why is it easier to do the multiplication in the new bases?
When you say easier, you mean faster?
Faster, yeah.
Yeah.
But you also do
I don't have intuition for that. It works. I don't know.
In regular matrix multiplication also don't count.
Oh, well, I do have some intuition. If in Strassen's original algorithm, you have the 3 UVW matrices, the 3 matrices that define the bilinear algorithm. If you have some repetitions here, you have sums that are repeating, you can do them, rather than doing them for each of the 7 linear combinations, you can do them once in your basis transformation, and then you don't need to repeat them. It's not exactly an intuition. That's technically what's happening. Yeah.
Maybe the better question is, how did you come up with this?
I didn't. Eli did. So what happened is we worked on a completely different problem on repeated squaring, where we tried to improve Bodrato's technique, and we had some ideas. And then Eli came one day and said, I think what we were trying to do works for matrix multiplication as well. And then I said, OK, maybe, and probably not, because we have a lower bound, so probably not. But it did. And then after we had that, OK, so what you see here is the 5 is due to the fewer linear operations, and this is for the 3 basis transformations. And this is a test on a laptop, multiplying matrices of size about 32,000. And this is a normalized. So 1 is what Vinograd's algorithm takes. So the second line. And we are about 16% better. So this is theoretically what we should have obtained. But these are small matrices, comparably small matrices, so you don't get the full speed up, but you do approach the 16%. And the next question was, can we do better? Can we further sparsify the operation? And the answer is no. And we generalized Probert's lower bound and proved that if you allow basis transformation on top of your bilinear algorithm, then the best you can hope for 2x2 base case algorithms is 12 addition. So this is as good as it gets. And well, we just hope that our new low bound holds more than 40 years now. All right. But then once there was some success with 2x2 case, we look into other algorithms. So this one, and maybe that one, and some that are not mentioned in this list. And thing is, the problem is NP-hard. Find the most sparsifying basis for a matrix is an NP-hard problem that's already in Gary and Johnson. But these are small matrices. These are fixed size algorithms. So you can either manually find them, or you can have a cluster or a supercomputer computer work for you and find new bases and improve existing algorithms. And you see here few algorithms. This is Strassen. This is base case of 2 by 2 multiplied by 2 by 2 using 7 multiplication. This is Smirnov's 6 by 3 multiplied by 3 by 3 using 40 rather than 54 multiplications. And what you see here is the number of linear operations in the original algorithm. These are the linear operation in the new algorithms, and sparsified algorithms. And these are the expected speedups, the theoretical speedups. And since then, with another student, we found a few more algorithms, right? And let me go to the second challenge, which is fault tolerance. All right, we already saw that one. So what solutions do we have today? The first solution we have is checkpoint restart-like solutions. This means that you dump the entire machine, state of the machine every few hours or minutes or seconds, and then every time you discover an error, either a node, a CPU stopped working, or you manage to somehow verify that you have a soft error in your computation, you just restart to the last saved state. This is very robust but expensive. You have to buy a large set of disks that work fast enough, and it increases the runtime significantly. There are better solutions. These are tailored solutions, algorithmically tailored solutions, where you encapsulate every function, every computation with traps and verifiers and make sure that everything works properly. If you do this right, you can take an algorithm and convert it into a fault-tolerant algorithm with resource overhead on the time and on the processor, a number of processor which is quite small. But this is hard work. It's hard enough to program. It's even more devastating to program in parallel. That's me saying. And doing that while worrying all the time, maybe this function didn't work properly, that's almost impossible. So people do that when there are no other options. So the goal here is to obtain the best of both worlds. So fault-tolerant, robust fault-tolerant general purpose, which is at the same time obtained automatically. You don't have to take care of each algorithm separately. We had previous success, so we have reason to have hope, both in the storage and in the communication domains. We have error correcting codes embedded in memories, hard drive, and communication channels in a way that is cheap and transparent. Can we do that for the computer gym? That's harder. Why is it harder? Because in the communication and storage case, everything looks the same. It doesn't really matter what you save or what you communicate. It's not the same. The computation graph can have complete different structure and may be much harder to defend. All right. Let me give just a glimpse on two or three ways how you can obtain fault tolerance automatically. If your computation graph has lots of repeating structure, like in matrix multiplication, FFT, maybe sorting and other algorithms, then you may be able to combine it with an efficient error correcting code to obtain a new computation graph which computes the same thing but guarantees fault tolerance. And we already demonstrated that on classical matrix multiplication, where the number of additional processors is the smallest possible. If your algorithm is irregular, either it is regular in theory but works on sparse inputs, so it like sparse matrix computations, or for other reason, then using error correcting codes automatically may be either not possible or very hard. Here we can utilize one drawback of this algorithm into our favor. So in these algorithms, typically, the CPU work very slow. So they work at 1 up to 15% of their machine peak, of their maximum performance. That means that we have an underutilized compute resource combined with very recent PCP-like structures that are not just linear, but linear with small coefficients. So like Elie-Ben-Sasson's X6, we may be able to apply that and obtain PCP merged with an irregular algorithms. And OK, I think I'll. All right. We know how to take recursive algorithms and make them into parallel efficient ones. In those cases, this seems like a good fit to automatically combine with error correcting code. And we have proof of concept. So we did that for Strassen's algorithm, obtaining the first fault-tolerant Strassen fast multiplication algorithm with almost optimal resource overhead. All right. I think I'll stop here. Thank you.